So now let's have a look at the basic principles of communications. I know this all sounds a bit theoretical, and maybe you know already some of the terms, at least I hope you know some of them. But let's repeat them just to make sure that you know when I talk about a certain thing like synchronous communication, you know what synchronous means. Okay, so let's start with this synchronous thing. So we saw we have end systems connected with a wire, for example, a link. And now we have two end systems. You cannot communicate with yourself. That's boring. And so we have two end systems, at least two or more, and there's synchronous communication. That means that sender and receiver are synchronized somehow. So, for example, if you access a system, let's say on an application layer, and you perform an action and many other systems perform the action, maybe you learned in programming something about synchronization points. So synchronous always means, okay, there's some action going on, maybe some communication, and then I have to wait. Maybe also wait until others did something, and then it continues. For us, in communication, the concept typically is in a way you will see that, okay, for example, I send something, and I always draw this using the so-called time sequence diagrams. You will see them quite often. So time flows from top to bottom, and we have always two or more communication partners, and then one partner is sending something. And synchronous means, well, you have to wait, for example. Okay, you send and you cannot continue sending until maybe the other side sends you something that maybe like, okay, I received it, fine, and then I can continue. We will also see synchronous communication when we look really on the wire, what's going on there. There we will see we send bits, and maybe part of the bits is for the communication from A to B over a certain wire, and then follows communication from some C to D, and then maybe, just to make it simple, it follows again A to B. So this is also synchronous communication because all the senders and receivers, they have to know exactly the time when A is allowed to send to B, when C is allowed to send to D, etc. So they are synchronized in time, and we will see how this is used in classical telecommunication systems. So, as written here, one of the examples is telephony, where we, on the physical layer, use synchronous communication. We'll see, so we have certain time slots where we squeeze in the data at a certain time, and then we know, just by knowing this is slot number 3, then we know, okay, this is communication from A to B. But also on the application layer, it's synchronous. So if I talk to someone, then I wait, and the other side will answer or ask something. And then I talk again. So also this ping pong is also a kind of a synchronous communication. We also have ways for asynchronous communication. Asynchronous, that means, okay, we can just go ahead. We don't have to wait. So if I want to send an SMS to someone, this SMS goes, very simplified, into the system, no matter if the other side reads the SMS, answers, whatever. If I want to send yet another one, this also goes to the other side. And yet another one also goes to the other side. Yet, and so on and so on. You can imagine. So This is asynchronous. So I can send as many messages as I want, and then maybe in the evening, this person reads all the messages and thinks, oh my, so many messages, whatever. Email is yet another example. You don't have to answer immediately. The other side can still send you new emails or all messaging, etc. So this is on the application layer. But also we have asynchronous sending. Also now let's go down, really down on the physical layer. For example, if I want to send a data packet, we will learn there are communication systems where you can just do it anytime. Well, I just send it. But we will learn that if we send a packet, then at least we have to write the address somewhere. Think of a letter. A letter definitely is asynchronous communication because you put it into the post box and that's it, but you have to write the receiver address on the letter. So we'll see many examples for asynchronous communication on different layers. So that's a basic principle, synchronous and asynchronous communication. What else? We have different types of communication channels. So the simplest form is called simplex. That means I can send information from A to B. I can continue to do this, but there's no way back. That's simplex. Because this channel does not allow the other direction. Examples for this: broadcasting system, the classical FM radio. You receive, but you cannot send back. So there are simplex systems, very simple things like pager systems for firefighters, etc. So very easy to handle. Okay, we will learn what this means for communication protocols, etc. There are half duplex systems. Maybe you know walkie-talkies. So you have to push a button to talk. But while you're talking, it's not possible for the other side to answer. So A can talk to B, and B has to wait. And then maybe later it's B's turn so that B can start talking to A. So that's called half duplex because you cannot use both directions at the same time. We'll see where we use this. For example, classical wireless LAN. In a classical wireless LAN, only one station can send data at one point in time. Otherwise, you have what's called a collision and data is destroyed. And then the most powerful, most flexible is a full duplex channel. There A can send data to B, and at the same time, B can send something to A. So some channels allow full duplex, some only half duplex, and this is something we also know from discussion groups. Usually discussion groups should be half duplex, otherwise we have collisions, chaos. Sometimes people try to use this channel as full duplex, and then no one understands anything. And teaching sometimes is simplex, but this is boring. So simplex is, for example, exactly what I'm doing right now. Videos, you can listen to the videos, but during our lectures, we at least I hope, we have this half duplex situation. Okay, so what else do we have? We have different ways of sending data, and we distinguish between the classical simple case of a unicast. So unicast means that from one end system, we send data to exactly one other end system. So unicast, that's a classical postcard, for example. Or in the internet, you send a data packet where you have an internet address, and this reaches exactly one host. There are other systems where A wants to send to everyone. That's called a broadcast. Then we will reach B and C and D, maybe at different points in time, but the network in between has to be able to distribute the data. So you see, although this looks pretty simple, unicast, broadcast, this means different things to the underlying network. Broadcast, well, that's a common scenario. I mean, if you have a TV station or radio station, because then the electromagnetic waves, they propagate through space to all receiving stations. So that space is a natural broadcast medium. But in our networks, in the internet, we don't have a broadcast meeting. Typically, we have wires, we have intermediate systems. So if we need a broadcast, we will learn we have to duplicate packets, maybe here at this intermediate system. So we duplicate the packets and send them along these different directions. Okay, unicast, broadcast. Both these are the extreme forms of communication. There's also something in between. That's called a multicast. So in a multicast scenario, we define a certain subgroup. So this is my subgroup. And although I send my packet into the network and theoretically it could reach all nodes, like our broadcast, the intermediate systems now have to be able to send the packets only to destinations that are members of this subset, of the so-called multicast group. So how do they know this? We'll find out. So multicast means we have a predefined group. Well, you can join this multicast group, but it's a group, it's not everyone. And the intermediate systems are able to figure out if this data belongs to a certain end system or at least belongs into a certain subnet. There are also systems like Anycasts. Anycast system, there potentially data could go to multiple end systems, but intermediate systems, the network, can select, for example, the nearest, the cheapest, the whatever. So one out of a group. So it's okay to have one. What are applications? We will learn, for example, that quite often computers have to know, oh, there is a name of a computer, or there's something, some information I want to know. Please give me the information. Then I do not care if this computer or this computer sends back the answer, as long as one out of a group sends back the answer. Anyone, I don't care which one, then it's fine. So maybe one of the computers overloaded, then the other can do the job, or vice versa. I don't care. There are some more scenarios, not that common, but just to mention them. One is the term is not used that often. It's kind of a convergence of data, concast. So data comes together and is forwarded towards a destination. Sometimes the intermediate system even can do some calculations on this. So think of, you have many temperature sensors, and those temperature sensors, whatever they measure, different values, and you're only interested in the average of the values, something like this. That you can already do some calculations in the network. Or you simply connect all the data and connect and forward all the data to a receiver. For some special purposes, we have a geocast. That means we forward data only to end systems in certain regions. This example may be Africa, And although, sure, we have connections to many other computers around the world, should rather go this way, but okay, so this is flat Earth. Although we have all the connections, etc., the network knows where the receivers are, and the network will only forward data to those receivers in a certain geographical location. And now you can think of only to certain brands of computers, etc., etc., etc. Okay, so now we learned a bit about how, and well, we can forward data, different scenarios, but it's quite important how those computers are interconnected, the end systems. And the examples just now I have just showed you, okay, they're somehow connected and just drawing some lines. But in real systems, it's quite important to think of what are the basic requirements for a network topology. So network topology, in the end, is just the graph where you have end systems, intermediate systems, whatever, and they are somehow connected. So that's a topology. So a graph. In the end, a graph with, as you know from theory, vertices and edges, and so this is a nice graph. And and somehow our data, if we send data here from A to some other node B, then somehow this data has to find its way through the network. So that's a topology. But if you look at these examples, we see we need certain requirements. So if we build a worldwide topology or a campus-wide topology, the topology should at least tolerate failures. So here you see I can send data from A to B. But what happens if this link fails? So we have a failure. Then there should be another path available. Then maybe data takes another path from A to B. So we should tolerate certain failures. We have to have several paths between a source and a destination. Okay, so now we may think, so maybe we connect all the nodes with each other. Okay, we will see that's a bit too expensive. So additionally, so how many links or what capacity do we need for a link? We know that a link is between two intermediate systems, typically shared, because you have many connections coming in, connections going out, and then you have a link in between. So, okay, different connections share this link. And so, as you saw, maybe we have different paths. How many do we need? Well, maybe not too many, because everything has to be cost effective. We should be able to share links for different connections, but we cannot install arbitrary high number of links or just high capacity. So it's always, well, we have to balance this. So enough for sharing. The sharing must be possible. It must be cost effective. It should be not too high, but it should be also not too low. Because if we have too few links in a network, then all the data, or majority of the data, will flow over this link. So if we have only a certain link, that this is heavily loaded, and so are the nodes, and their maximum capacity of the nodes. So this is why we need also other links, maybe to reroute traffic. So it has to fit. Not too many links, too expensive, not too few links, because this would overload the systems. Okay, you see, there's always a trade-off. But how do these topologies look like? And do they fulfill these requirements? Tolerate failures? Can we share them? What is the load? Well, just to give you some impressions of typical topologies. So, yeah, in an ideal world, we have a fully meshed network. That means all the nodes can reach all the other nodes via direct links. Great. Isn't that nice? So I can directly send my data to all the nodes in the network. Well, you can imagine this does not work for large networks. This works for small networks. For example, a wireless ad hoc network, fully meshed. All the nodes can reach each other, but not for large networks. Okay, what else? Just let's say to contrast that, we have a chain of nodes. So you see, okay, to reach from A, maybe node X, we have to forward data along the whole chain. Well, chains are cheaper. Just compare the number of links between the full meshed network and the chain topology. So it's cheaper. But what happens in case of a link failure? The network breaks apart. In a full meshed network, if there's a link failure, well, you can always reroute traffic. So that's no problem just to reroute it and say, okay, then we simply take another way. If the direct connection is not available anymore, you see, then we take a detour. Simple. That's the same for road networks, etc. Okay, but for a chain, this doesn't work. So, what could we do? Well, we can create partial mesh structures. And this is one of the most common type we see in networks. We cannot afford this full mesh. That's way too expensive, no matter what currency you choose. So way too expensive. But chains, they're not really fault tolerant, so partial mesh. So if now, for example, a link breaks, okay, I have to make a detour. That's not as short as in the full meshed case, but it works somehow. So partial mesh, that's typically the way to go, that you have at least 2-3 alternative paths for all of the connections, but you don't have the full mesh scenario. And then we have some more specialized topologies, star and tree. So star topology, this is something we typically find, for example, in buildings. So if you have a building with different floors, then there's some wire coming in from the internet. Then you have the first intermediate node here. That's the router. We just saw our DSL router. And then depending on how many computers you have, etc., you could have something like, we will learn some more details about this, a switch on each floor. And this switch then in the end connects in a star topology to all the end systems on the different floors. So you have many stars, a star for each floor, and in the end, you have this kind of a hierarchy, a star from the route's point of view to the switches, and then stars from the switches to the end system. We also have tree topologies. That's the case for the classical cable network, for cable TV, where you distribute your cable TV program and you have some nodes in between, then you just distribute it. So tree topologies, they are well known also from the classical USB connections, etc. Okay, so these are different typical topologies. Depending on the topology, we will need different protocols, different way of how we handle communication. So let's come to some questions and some tasks. So think of the pros and the cons of synchronous and asynchronous communication. So what is good? Why should we go for synchronous? But maybe what are the disadvantages? So when do we use asynchronous? Think also of applications for synchronous and asynchronous. So you should know some. Think also of typical applications for these simplex, half-duplex, and duplex channels. So not all applications can be used for all different types of channels. Then think of our Unicast, broadcast, etc. schemes. What could be applications for? Some of the applications, they simply do not work with Unicast or are not very efficient. And then compare the different topologies. Now in terms of sharing, how do we share links? Are they resilient? What about the capacity we need per node? There are big differences. So what are the pros? What are the cons? When do we use which type of topology?